This is the third part of Lesson 25 in Heat Transfer. Lesson 25 launches the Thermal Radiation Heat Transfer Unit. In the last part of the lesson, we discussed applications in which thermal radiation is important. In this lesson, we will begin to explore the fundamentals of thermal radiation heat transfer and discuss the 4 physical processes associated with radiation heat transfer between surfaces. By the end of this lesson, you should be able to list these 4 physical processes. You should also be able to explain what the property is called that describes each of the 4 physical processes. And finally, you should be able to recognize the variables used to represent each property. On with the lesson.
There are basically 4 processes that you'll ever see in radiation heat transfer. Right? Emission, absorption, reflection, and transmission. So it all boils down to one of those 4 things. So we have to understand what they are. I added this 4th column after I printed your handout. So you definitely want to include it, though I think it's important. So let's talk through what these different processes are, and then I'll link them to the property that goes with that process, and also you see the radiative flux. When I think about these processes, I think about it in terms of a surface. So I'm going to draw a surface here. So this could be like a glass surface. It could be the surface of a table, but the surface is some interface between typically a gas and a solid is the way that I think. In terms of this class, that'll be a good way to think. Right? Or it could be between a vacuum and a solid if you were in space. So you could have a vacuum over here, but it's a surface. And to start with, we're going to say that the surface is semi-transparent. And the surface has some temperature T, right? So it has some temperature T. If you want to say T sub S for surface, that's okay, but it has some temperature T. And because it has a temperature, it is emitting radiation. Any surface that has a temperature is going to emit some radiation by the very nature of its temperature, because its temperature is playing the popcorn game with the electrons. And so because of that's happening, photons are going to get spit out. We call that emission. So there is emission of energy due to that process. And the energy that's emitted is called the emissive power E. So emission is characterized by this variable E, emissive power. Now, I have to admit, I really don't like this term that we're given, but it's historically, this is what it's been called, because at least in this class up to this point, if I say power, you usually think of something, hopefully you think of something in units of watts, right? It's like this power has units of watts, or horsepower, BTU per hour. But in the context of radiation, when someone says emissive power, they actually mean something with the units of watt per square meter. So emissive power is actually a flux. So it's really confusing. I'm sorry about that. I'll work on changing it over the rest of my career. How about that? Okay, but this is what's been handed to us, and this is the language that your textbook uses. So I'm trying to be consistent with it. If I could have changed it, I would have started from the very get-go, and we would have been calling it emissive flux. But it's emissive power by the historical development. Okay, so just don't be confused by that. Emissive power E has units of watt per square meter. That's the emission side. Okay, and then we have the other 3 processes that are all related to the irradiation, right? And irradiation is just the sum of all of the radiation that is incident on a surface. So irradiation is, I think of it as a shortened form of incident radiation, where you take the I in incident and you slam it up with the radiation to call one thing irradiation. It's like we got tired of saying incident radiation over again. So instead of saying incident radiation, we just say irradiation, and we forget the incident part. The incident part, I guess. Incident. Irradiation, incident radiation. So that's radiation that's coming towards the surface. Okay, we call it, we use the letter G, right, to denote irradiation. Three things can happen with this radiation streaming at the surface. Three things can happen. The one thing that can happen, we can have some of this radiation reflected. So this is reflection. It's like the energy gets turned around and sent back the other direction. And it's characterized by the property reflectivity. And the reflectivity, in fact, all of these properties take on a value between 0 and 1. So if you want to note that somehow, 0 is less than epsilon, rho, et cetera, it's less than 1. Right? The amount that's reflected is given by rho times G. Think of the reflectivity as almost like a fraction. It's like the fraction of the radiation that gets turned around and sent back in the other direction. That's one possible thing that can happen to the radiations. The other possible thing is that can actually be absorbed in the surface. So it can be taken up, right, by the surface. It's like it terminates there. So we have absorption. Characterized by the absorptivity, right? And the amount that is absorbed is given by alpha times G. So that would mean it's actually an increase in the thermal energy state of the interface. You want to think of it that way. The third possibility is that the energy just moves through the surface. That's called transmission. And the amount that's transmitted is given by the transmissivity. And if you multiply by G, that is the transmitted energy, tau times G. It makes sense what these four processes are. Emission is the creation of photons. Right? Photons come out because of emission. Absorption is the destruction of photons. The photons are turned back into the thermal energy of the matter. Reflection and transmission, the photons keep on going, right? When radiation is reflected, it's still photons, they just get redirected, right? They get sent off in some new direction. Transmission, the photons still also exist, right? They pass through. It's like they pass through unaffected, okay? That makes sense? So emission is the creation of photons. The only way that the photons can be terminated is through absorption. Okay, hopefully you can kind of see that there's a relationship between reflection, transmission, and absorption. Because that's the three possible fates of the radiation, if we add those three things up, we got to get back to the original thing. Agreed? Like it all started as G, and it went into one of these three things. You can almost think of it like a little thermal circuit, right, where there's a little node right here, and G went in, and absorption, transmission, and reflection came out. So if you add them all together, there's a common G in each term, right? Which means 1 must equal alpha plus tau plus rho. This is always true. If you add up the reflectivity, the absorptivity, and the transmissivity, you have to get to 1. Everybody see that? Does that make sense? Okay. There are also surfaces called opaque surfaces. In opaque surfaces, there is no transmission. The energy is either absorbed at the surface or it's reflected at the surface. So tau equals 0 in that particular case. And I'd say the vast majority of surfaces that we'll consider in 376 are opaque surfaces. You want a really nice application of semi-transparent surfaces, take my solar technologies class and we'll deal with them. Because that's what glass covers are. Greenhouses, Aaron, that's right. Transmission of visible light through the glass, but then you'll see the glass doesn't transmit infrared light. So the visible light transmits through, but then it can't get back out. That's what how a greenhouse works. Any questions on this? I know it's a lot of jargon. Radiation is very jargony. And so it might be helpful to create like a little glossary or a list of terms for yourself and their definitions for a quick little reminder. This slide is a pretty good one though, I'd say, in terms of being a good glossary.